In this last section of Chapter 4, we're going to talk about combinatorial proofs, which are sometimes called proofs by double counting. Double counting can mean different things in different contexts. We talk about it a little bit with principle of inclusion-exclusion when we mean something entirely different in that context. So it's more often that I'll call it a combinatorial proof. Now, a proof by double counting, or a combinatorial proof, is one where we justify that a particular equation is correct by showing that each side of the equation is giving a way of counting the exact same quantity. So this is different from the bijective proofs we saw before, where we found a bijection from one set to another to conclude that the cardinalities of those sets were the same. This time, we're trying to show an equation is true, and we're going to do it by showing each side of that equation is really counting the same set, or the same object. So let's go through an example together. We're going to prove the following binomial identity. It says n choose 0 plus n choose 1 plus n choose 2, all the way up to n choose n. If you add it all up, you get 2 to the n. And we're going to prove this using a combinatorial proof. Now remember, we saw this result already. If you head back to all the way back here, Pascal's triangle. In class we had talked about how if you add up any one given row of Pascal's triangle, add up all the elements of that row, you'd get 1. Here you'd get 1 plus 1 is 2, 1 plus 2 plus 1 is 4, 1 plus 3 plus 3 plus 1 is 8. This would be 16, and on, right? These are all powers of 2. This is 2 to the 0th power. This is 2 to the 1 power, 2 squared, 2 cubed, etc. So we've seen this sort of suggested to us already that if you add up n choose k for every possible value of k, starting at 0 and going up to n itself, that you end up getting 2 to the k. We're going to prove this now, and we're going to do so using a combinatorial proof. Now, a combinatorial proof is one where we show that an equation is true by showing that each side of the equation can be used to count the same quantity, right, or to find the cardinality of the same set. So when you see something like this and you want to prove it combinatorially, you should be asking yourself, well, what is each side of the equation counting? And 2 to the n should jump out at you from chapter 1 as counting many different things, but in particular, 2 to the n counts the number of binary strings of length n. And remember, a binary string is sometimes called a bit string. It's just a string of zeros and ones, and that string has length n. Okay, so there's 2 to the n many binary strings of length n. We know this from the multiplication principle. So, a combinatorial proof would be one in which we show that the left-hand side is also counting the number of binary strings of length n. Okay, if we can show the left-hand side and the right-hand side are both counting the number of binary strings of length n, then we'll know that the left and the right-hand side are equal, and we'll show that this equation is indeed correct. Okay, so how do we show that the left-hand side of the equation is actually counting the same thing? It's counting the number of binary strings of length n. Well, it's a sum, right? It's a sum of a whole bunch of n choose k's, and so it's probably going to make sense for us to try and break up the number of binary strings of length n by cases, right? Hopefully this will count the number of binary strings of length n with some property, and this will count the number of binary strings of length n with a different property, etc., all the way down the line. Okay? So, it would make sense then to try and think about all of our different binary strings. Let's just look at a particular example. We'll say n equals 5. Our binary strings of length 5 are things like 0, 0, 0, 0, 0, or 0, 0, 0, 0, 1, or 0, 0, 0, 1, 0, or 0, 0, 1, 0, 0. Oh, I don't want to have to do this all, right? There's going to be 32 of them. There's going to be 2 to the 5th power of them. So I don't really want to list them all, but I do want to break them up sort of into cases so that each group is counted by n choose k for some k. In this case, it'd be 5 choose k for some k. And so the way that we're going to do it is we're going to look at how many zeros a particular string has. Right, this string here, this string has, it has all zeros. It has 5 zeros. These strings here, if I continued trying to do this in an organized way, these strings here all have exactly 4 zeros. Okay, once I listed out all of the strings that have 1, 1, and 4 zeros, and then I would have to list out all the strings that have 3 zeros and 2 ones, right? 0, 0, 0, 1, 1, or 0, 0, 1, 0, 1. Right, I'd have to count out how many binary strings have exactly 3 zeros. Or 2 zeros. I'm not going to list them all, but they're there. Or 1 0. Or finally, we'd have the case that our string has no zeros. This would be the string 1, 1, 1, 1, 1. Okay. And so what we're going to do is we're going to count how many there are of each type of string here. Every binary string of length n has some number of zeros, either 0 zeros or 1 0 or 2 0, all the way up to n many zeros. And we're going to count how many there are of each type. So, how many binary strings of length n have no zeros? Well, the only possible binary string that satisfies this would be the string 1, 1, 1, 1, 1, 1, 1, right? All ones. And so there's going to be exactly one such string, but in particular, we can think about this as saying, let's say n choose 0, or one such string. Because we have n spots to fill, right? And we're going to choose none of them to fill with a 0. Every other spot is going to be filled with a 1. All right, now look at the second case. How many binary strings of length n have exactly 1 0? Well, out of your n many spots, you need to choose which one of these spots do you want to fill with a 0. There's n choose 1, I'm doing this sort of too big, but there's n choose 1 many ways to choose one spot out of n to fill with a 0. So there's n choose 1 strings that have exactly 1 0. How many bit strings of length n have exactly 2 zeros? Well, n choose 2 many strings, which is whatever it is. It doesn't even really matter what it is. We're trying to show that we can add these all up at the end, and so I can just sort of leave them as n choose something. I don't really have to simplify each time. But there's n choose 2 such strings. And in general, let me make a little space here. Whoops. In general, come on. There we go. There are n choose k many binary strings or bit strings of length n with exactly k zeros. And that's going to be true for every k between 0 and n. And so the left-hand side is counting the total number of binary strings of length n. It's just breaking them up into cases and saying, well, there's this many that have no zeros, and there's this many that have 1 0, and there's this many that have 2 zeros, etc. So in the end, n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n is going to tell you the total number of binary strings of length n altogether, because every single string falls into one of those categories. And so the sum of them all together will give you all of the possible binary strings of length n. And since both of those are counting, both this expression here and the expression 2 to the n are both counting the number of bit strings of length n, we can conclude that they are equal to each other, which sort of proves what we were trying to prove combinatorially. Now, maybe you could have proven this algebraically. Maybe you could have said, I know that n choose 0 is n factorial over 0 factorial times n factorial. And n choose 1 is n factorial over 1 factorial n minus 1 factorial. all the way down the line until you get to n, choose n, which would be n factorial over n factorial 0 factorial. Maybe you could have shown that this was true algebraically just by somehow grouping these into one big fraction and doing some kinds of cancellations. Maybe this is possible to do. But first of all, it's going to be super, super messy. And second of all, it's not really nice. It's not a pretty proof, and it's not a satisfying proof. If you can prove something combinatorially, if you can show an equation is true by saying, oh, look, they're both counting the same thing. Both sides of this equation are counting the number of bit strings of length n in this case. It's telling you more about what's going on sort of behind the scenes, right? It's giving you more insight into why this particular equation is true in a way that an algebraic proof might not really tell you, right? You potentially could do some really messy algebra to show that this is true, but it doesn't really tell you anything interesting about what's going on behind the scenes, about what these things are counting. And so combinatorial proofs can be a really beautiful way of showing that certain equations are true.